Start.
Okay, so good evening, everyone. My name is Benedict Aqua. I'm a second year geological engineering student, J2, and today I'll be taking you guys through fluid mechanics. So, shall we pray? Father, in the name of Jesus, we thank you for today. We pray that, O Lord, as we start this lesson, you will give us understanding and knowledge that at the end, glory and adoration will give you unto your name. These and many other things I ask through your Son, Jesus Christ. Amen. So, today, unfortunately, we don't have much time on our hands, so we'll try to speed things up a little, hoping to cover as much as we can. So, we'll start from the very beginning. So, first of all, what is a fluid? We are doing fluid mechanics. A fluid is a group of molecules with relatively large distances between them, and these compounds or groups of molecules have attractive forces that are smaller than that of solids due to the large spaces between the molecules. So we can also say a fluid is a substance capable of flowing and has no definite shape but assumes the shape of a container. And between, so we can say that both liquids and gases are fluids because they take the shapes of the containers they are placed in. And so let's go to what is fluid mechanics. Fluid mechanics is the science of the mechanics of liquids and gas based on some fundamental principles employed in solid mechanics. So fluid mechanics is divided into fluid statics, fluid kinematics, and fluid dynamics. So the focus of this course is going to be fluids that are not in motion for the most part of it, fluids that are stagnant at one place. So let's move straight to, okay, so let's look at body forces and surface forces. So body forces are forces on a body whose distribution acts on matter without requiring direct contact. Examples are gravity, magnetic force, inertia, etc. We also have surface forces, which arise as a result of direct contact of a body, direct contact on a body. Examples are friction, frictional force, pressure, etc. So we want to look at some fluid properties that will be useful in our study of fluid mechanics. So we have the extensive and the intensive properties. The extensive are the properties whose substance depends on the amount of substance present. So something like volume. Volume depends on the amount of, let's say, fluid in a container. So it depends on the amount of substance present. While the intensive properties are those that are independent. So something like pressure, something like viscosity, surface tension, they don't depend on the amount of substance present. So we want to look at some basic formulas we'll be using throughout the cause. One is density, which is equal to mass over volume. And the unit is kilogram per meter cube. We'll also be looking at specific unit weight. Specific unit weight is equal to weight over volume. And we know weight is equal to mass times acceleration due to gravity. And so, looking at this, you can see this appearing over here. So that is the same as density times, sorry for my writing, and this, the unit of this is kilogram meter per second squared. This. I think this will look much better. Okay, so we also have something we call specific volume. Specific volume. That's equal to the inverse of density, which we can also say is volume over mass. And the unit is meter cube per kilogram. Yes. Okay. Now let's also look at specific gravity. So specific gravity is we can say it is the density of a substance over the density of water, or the weight of a substance with respect to the weight of water. So it goes either way. Okay, so now we mentioned earlier that we are going to look at some fluid properties, and one of the first of them is viscosity. So viscosity. And viscosity is basically the resistance of a fluid to shear stress. Yes, the resistance of a fluid to shear stress. And viscosity varies inversely with temperature, while it varies directly. The viscosity of some liquids vary inversely with temperature, whilst others vary directly with temperature. So before your midterm, one thing that will be of importance to you is to basically how to prove the formula for viscosity. Yes, so assuming we have this diagram, right? Then we have so we realize that if we have something like this, okay, there is an angle formed over here, and when we take so this is x, this is y. When we take tan of this angle, we are going to get x over y. But then this angle is very small. So when an angle is very, very small, it is basically the same as the angle. So we have this, sorry, it's phi. The angle is phi. So now this phi is equal to x on y, which is the same as your shear strain. Right. So if you want to find rate of shear strain, rate simply means per time. So this is going to be your rate of shear strain is going to be this divided by time, which will be the same as this. So this becomes rate of shear strain. But then we also know that velocity is equal to distance traveled over time. And we can see that over here. This portion, you can see this. So we can say that our rate of shear strain is equal to u over y. So this is an important piece you should take note of. Sorry. Yes. Okay. So now when we take the shear stress at any point in a fluid, which is tau, it is directly proportional to the change in velocity over the change in the displacement. And this forms the fundamental formula for viscosity. So we can see that this shear stress is this formula, where your mu is your dynamic viscosity. So mu is dynamic viscosity. So this formula clearly explains Newton's law of viscosity. And another thing to take note of is that kinematic viscosity, let me just make so then kinematic viscosity is equal to your dynamic viscosity over your density. So this is kinematic viscosity. Okay. And the unit for viscosity, the dynamic viscosity, is Newton second per meter squared, while the unit for kinematic viscosity is meter squared per second. Please let's take note of that. Okay, so let's look at surface tension and capillarity. Surface tension, capillarity. So we have surface tension, then capillarity. So for surface tension, it's like a force. It causes liquids to behave as a stretched elastic skin. That's the surface of water. So it occurs at the surface of water. And so we would want to show how surface tension relates to pressure. So when we take a fluid, first of all, we know that pressure is equal to force over area. Therefore, the force is equal to the pressure times the area. So if we consider a fluid, the pressure being P, the area would be, let's say the fluid is in a cylindrical container. Then the force, or the force due to pressure in the fluid, will be the P times pi r squared. Right? And also, we can say the force due to surface tension. Surface tension acts at the surface of the fluid, and it acts opposite to the direction of the force that is due to internal pressure in the fluid. And so that the formula for that, so the force, okay, this force is due to, let's make this force due to internal pressure. Now force due to surface tension at the surface is going to be 2 pi r times the surface tension. And so in equilibrium, these two will be equal to each other. So now you can say that pi r is equal to 2, sorry, so P, okay, and now with a change of subject, we now have P is equal to 2 times the surface tension on R. So this formula relates pressure and surface tension. So let's take an example. So the example is, if air is introduced through a nozzle, into a tank of water to form a stream of bubbles, if the bubbles are intended to have a diameter of 2 millimeters, so the diameter of the bubbles is 2 millimeters, calculate by how much the pressure of the air at the nozzle must exceed that of the surrounding water. So we have diameter here being 2 millimeters, and then we have the surface tension to be 72.7 times 10 exponent minus 3 Newton per meter. So in this case, you can see that the diameter is in millimeters, but then the surface tension has per meter. So that means we have to convert the millimeters to meters, and that is going to be equal to 2 times 10 to the power minus 3 meters. Okay, so we are looking for pressure. What do we have? We have surface tension, we have diameter, and we know that radius is 2 times the diameter. So if the diameter is 2 times 10 raised to the power minus 3 meters, then the radius is going to be equal to 1 times 10 raised to the power minus 3 meters, because we divide by 2. So now, if we want to calculate, we have P is equal to 2 times 72.7 times 10 raised to the power minus 3 all over the radius 1 times 10 to the power minus 3. And when you solve that, you should be getting 145.4 Newton per meter squared, since pressure is force over area. So you should be getting 145.4 Newton per meter squared. Okay, so now let's go to capillarity. Capillarity also involves surface tension, and so using this illustration, we have something like this. And then if we look at this angle here, theta or phi, so it can be theta. Okay, let me just make it theta. So this angle here is theta, and this is the force that is coming from surface tension, right? Now at the same time, this is the force, so we have this force here being 2 pi r, and then your surface tension, as we demonstrated earlier. And now we have here your gamma pi r squared h. And so this, when you simplify this, you realize that the unit of this is Newton. So your force can also be expressed as rho g times volume. So this component here is your volume, and then, as we said earlier, gamma is equal to rho times g. So now we have the force due to pressure inside the column, let's say of a cylindrical tube. And so we have gamma pi r squared h is equal to 2 pi r sigma. And so we also know that d is equal to r over 2. So we can have gamma pi d squared over 4, because you square this r over 2. So you square this r over 2, and now h is equal to and also this here represents the circumference of a circle, and it can also be written as pi d. So over here we have pi d sigma. So now, if you want to find the capillarity, which is basically the rise of the fluid in a medium, which is our H, what we are looking for, we are going to have 4d sigma all over gamma times d. Yes, but then I forgot to mention something. So with this force here, it's acting through a certain angle. So if we want to find the equilibrium between them, they must act through the same axis. So this will now be cos theta, because when you resolve it onto the y-axis, the angle reduces. Sorry for not adding that. So this also here is cos theta. So this will be cos theta. Yes. So this is your formula for your capillarity. This is your formula for capillarity, where H is capillary rise. Your sigma is your surface tension. Your d is your diameter. And then your gamma is your weight density of the fluid. Okay, so let's take an example. So what is the diameter of a cleaning glass tube required so that the rise of water at 20 degrees Celsius in a tube due to capillary action is less than H equals 1.0 millimeters? Oh, sorry, it seems the question we have some parameters missing. So let's continue. Let's continue. If I find the complete question, I'll come back to that. So we are moving on to, okay, let's solve a question on viscosity. Let's solve a question on viscosity. Solve a question on viscosity. Okay, so example, let's solve question on viscosity. Okay, so it says if the velocity distribution over a fluid plate is given by this expression, U is equal to 2 on 3y minus y squared, where U is the velocity in meters per second at a distance of y meters above the plate. Determine the shear stress at y equals 0 and y equals 0.15 meters. Take dynamic viscosity to be 8.63 poises. Okay, so we are seeing a new unit over here, poises. And for poises, 1 poise is equal to 1 over, so it's just 1 over 10 Newton second per meter squared. So that means if you are converting it into the normal unit, you are going to divide your mu, you are going to divide whatever value you are given in poises by 10. So that means our new dynamic viscosity is going to be 0.863 Newton second per meter squared. Okay, so now let's go straight away. So we know that the formula for shear stress is equal to this, which is mu times du over dy. And here you can realize that the equation for the velocity is given in terms of u and y. So that means when we differentiate this, we are a step closer to solving the problem. So first of all, we are going to differentiate u. So du dy is equal to 2 over 3 minus 2y. 2 over 3 minus 2y. And so the question first asks us to find the value of this shear stress or this viscosity at y equals 0. So at y equals 0, du dy, so let's say du dy where y equals 0 is going to be equal to 2 over 3 minus 2 times 0, which is the same as 2 over 3, right? And so this 2 over 3, we can, okay, let's leave it. We'll leave it like that. So this is 2 over 3, but then we are not done. The formula is mu times du dy. So that means now we have to multiply 0.863 by 2 over 3. And that should be giving you 0.576 Newton per meter squared. So you realize that this is in Newton per meter squared, so it's like pressure. So that is for your the first part of the question. Now it says we should find the viscosity when y is equal to 0.15 meters. So that means we are going to find du dy at y equals 0.15, which is going to be equal to 2 over 3 minus 2 times 0.15, which is going to be equal to 2 over 3 minus 0.3, and that should be giving you something like 0.367. So now to find the shear stress, we are going to now multiply this 0.367 by our mu, which is 0.863, and this should be giving you 0.317 Newton per meter squared. So this should be your final answer for this question. Okay, so I want us to take one more question, then we move on. Okay, so for the next question, we have a plate which is 0.025 millimeters is distance from a fixed plate. So that means we have a plate that is fixed, so the fixed plate, and we have another plate. I think so this plate is subject to motion, whether in this direction or in this direction, subject to motion. So we have two plates, and it says the distance between them is 0.025 millimeters. So we can say that this is the dy, which is the change in the distance between them, which is 0.025 millimeters, and it moves at a speed of 60 centimeters per second. So that means our u velocity is 60 centimeters per second, and it says that it requires a force of 2 newtons per unit area to maintain the speed. So this 2 newtons per unit area is basically pressure, because it's force over area. So this is the pressure required to maintain the speed. It says now determine the fluid viscosity between the plates. Determine the fluid viscosity between the plates. So we'll start okay, so first of all we have our okay, so let me clarify. I think I mixed something up as I was speaking. This tau we are looking at is shear stress, and then the mu is the viscosity we are looking for. So please, sorry for that, please don't get confused. This is your dynamic viscosity. It is still viscosity. So if you are asked to look for viscosity in the question, it's your mu, but then your tau is your shear stress. Yeah, so okay, so please we can continue. Okay, so we have our distance between plates to be 0.025 millimeters, but then this is not in meters, so we want to convert everything we have here to standard units. So this is going to be 0.025 times 10 raised to the power minus 3 meters. And then we also have our velocity, which is in centimeters. We want to convert it to meters. So this is also the same as 0.6 meters per second. right? So we have this to be 0.6 meters per second. Okay, and now we want to, okay, so now our change in velocity is going to be 0.6 minus 0, because the initial velocity was 0, unless otherwise stated. Our initial velocity was 0, therefore the change in velocity is 0.6 meters per second. So now let's start solving. So we know our formula is this, right? And what do we have? We have our tau, we have our du, we have our dy. So that means now we can find mu. And our tau, since it's in pressure, which is Newton per meter squared, this is our tau. So now we say that 2 is equal to mu times 0.06 all over 0.025 times 10 raised to the power minus 3. So when we do a change of subject, we are going to have 2 times 0.025 times 10 raised to the power minus 3 all over 0.6. And when you are done solving, you should be getting 8.33 times 10 raised to the power minus 5 Newton second per meter squared. So please, this should be your final answer. Okay, so I think we can move on to the next thing. So now we want to look at hydrostatic pressure. We want to look at hydrostatic pressure. So hydrostatic pressure. So hydrostatic pressure is basically pressure at a given point in a fluid. And there are some two major properties of hydrostatic pressure which you should take note of. Properties of hydrostatic pressure. Please take note of this. There are two. So it says hydrostatic pressure is a compressive stress and always acts along the inside normal to the element of area, meaning that hydrostatic pressure is always going to act perpendicular to the medium, the surface of the medium in which it is acting. And the second thing is that the magnitude of hydrostatic pressure at a given point does not depend on the orientation of the surface. So it doesn't matter if it's passing through a medium like this or it is going through a medium like this. Once their heights are the same in both of them, in 1 and 2, the pressure is going to be the same at, let's say, the same point. In both of them, it's going to be the same pressure. Okay, so let's move on. So now we want to look at the basic differential equation of hydrostatic pressure. So you know that pressure in a real world acts in all directions, x, y, and z. So this fundamental formula is as stated. You can take note of this. We won't be using it in calculations, but it's going to help us as we derive some formulas. So this is your main formula in differential form. We are going to use this to come across other formulas. So assuming we say that u is a function in terms of x, y, and z, we can use this u to replace all of this, because u is a function that contains x, y, and z. So we'll say all this is now u. So now we say that this formula now becomes this. And so if we integrate this, we are going to get we're going to do integration. We're going to have 1 on rho times p is going to be equal to u plus going to be u plus c. And so multiplying through, we are going to have p is equal to rho of u plus rho of c. But then c is a constant. We don't know that constant. So whether we multiply through by rho or we don't multiply through by rho, it is still a constant. We don't know the value of that constant. So that can still be written as rho of u plus c. But then we want to find the value of c because it's a constant. This is the equation we are deriving. We don't know what the value of this constant is. So now let's try to look for conditions that are known to help us determine the value of c. So let's say we have a certain pressure P naught, and we have the expression in terms of u as u naught. We can now say P naught is equal to rho u naught plus c. So these P naught and u naught, we can say they are external parameters in terms of pressure, right? So now when we make c the subject, we are going to have c is going to be equal to P minus rho u naught. So now that we know the value of c with these known conditions, these are known. So in case you have a question, they will be known. So since we have these known parameters, we can now put it back into this equation. So now we can say P is equal to rho U, rho U. I think let me scroll down. So we have P is equal to rho U plus P naught minus rho U naught. So when we simplify this, we're going to have P is equal to P naught plus rho then U minus U naught. So this is the general equation of hydrostatics in integral form. So the previous one we looked at was in differential form. But then this is in integral form. Okay. So now let's consider hydrostatic pressure when gravity is the only force acting on a body. So if we have a certain body in a container and gravity is the only parameter acting on the body in a fluid, using the basic differential equation that we had, we have this. And so if gravity was the only parameter acting on the body, we know that the z-axis sorry let me we have the z-axis going this way, then we have our y-axis going this way, and our x-axis going this way. So now when you look at this, assuming this was in like a 3D figure, right? We can say that this object will be moving only in the negative z direction, because z is going this way, so that means negative z will be in this direction. So if gravity is acting on the body, it means it's going to move only in the z direction downwards, ideally. And so that means movement in our x-axis here is 0, movement in our y-axis is 0, but movement in the z-axis is minus
Sorry.
So please, I was drawn to a concern. I'm very sorry, I made a mistake here. So it's actually um radius that is diameter over 2. I am very, very, very sorry for that. Very sorry. Radius is diameter over 2. Thank you for correcting me. So we are going back to what we were doing. Yes. So since in the z direction the only force influencing this is our acceleration due to gravity going the negative z-axis, this g becomes negative. So now if we want to rewrite this formula, this differential formula, it is going to be as follows: minus g dz, right? And we can continue in this line and have rho g dz. So that means now we have, integrating this, we have p to be equal to minus gamma z plus c, since this is an indefinite integral. So now we want to find the value of c. So let's take some known conditions. So if we go to the surface of a fluid, if we pick the point on the surface of a fluid, the z is 0 because distance moved at this surface here, distance moved in this z direction is 0, and at that distance we can say our pressure is equal to P naught, which is an external pressure. So now if we substitute this into the formula, we have P naught equals to C. So that means now our formula now becomes P is equal to minus gamma Z plus P naught. And let us say that that distance moved in the negative z direction, let us call it h. So that means h increases as you move downwards, right? So if we say that that negative z, let's make it h, it means our formula now becomes gamma h plus p naught. And this is the fundamental equation for hydrostatics. This is the equation that we are going to be using mostly, and we will also have various forms of this equation. So now we can say that when we define the terms, P is the absolute pressure, then we have gamma H as the body pressure, the pressure as a result of the body involved. So let's say it's a fluid, it is the pressure due to a certain height of fluid. And then we say P naught is our external pressure. It can be it can be atmospheric pressure, or it can be pressure from a fluid of different density. So these are the defined parameters for hydrostatic pressure. And so in the case where this external pressure is atmospheric, we have P to be equal to gamma H plus PA. So when we write it in this way, this becomes gauge pressure. The formula for gauge pressure or manometric pressure. Okay, so let's take an example. So we can, let's say, so oil with specific gravity (0.8) forms a layer 0.9 meters deep in an ocean tank that is otherwise filled with water at 10 degrees Celsius. The question says that the total depth of the water and oil is 3 meters. What is the pressure at the bottom of the tank? So for a question like this, first of all, one way to help you is to visualize this. So we can say that this is our water, this is our oil. And it says that the oil forms a layer 0.9 meters deep. Okay, so let me do it this way. So this height here is 0.9 meters. And it says that the total height of the tank is 3 meters. So the total depth of water and oil, or the total height of water and oil, is 3 meters. So that means that of water will be 2.1 meters. 2.1 meters. So now it says, what is the total pressure at the bottom of the tank? So we realize that there are 2 points where we can, there are 3 points where we can find pressure. We can find pressure here, can find pressure here, can find pressure here. Pressure at this point is obviously 0. Why? If we take the formula, P is equal to gamma H plus P naught. At point 1, you can see that the height below that point is 0, because that is the starting point of the fluid. So that is 0. And at this point, the tank is exposed to the atmosphere. So the external pressure on this point is atmospheric pressure. Although atmospheric pressure has a value, when you are using your gauge, when you are finding gauge pressures, what we are doing here, we are finding gauge pressures. So when you use any pressure measuring device, it considers atmospheric pressure as 0, because it's basically like you've not put the device in any fluid or any column of fluid, so 0. So for at point 1, pressure is 0. Now if we come to point 2, we have a fluid which is water, and it is there. We can find the pressure at the point where the oil and the water meet, because there is a depth, right, in a fluid. So we can say that this gamma, we know gamma is rho g. So we can say that the density of water, which we all know as 1000, times acceleration due to gravity, that forms your gamma, plus your P naught, this is gamma H, so you have to multiply by the distance through which is acting, which is 2.1 meters. 2.1 meters, right? And that will be plus your external pressure. In this case, the external pressure is still atmospheric pressure, because when you are coming down, you start from here and you come here. So that means the external pressure to this medium is the atmospheric, so it's also 0. So that now becomes your 1000 times 9.81 times 2.1. That should give you 20,601. You can say Newton per meter squared. And now we asked to find the pressure at the bottom. So that means we also need to find the pressure at point 3. And the reason why we found the pressure at point 2 was because at point 3, the external pressure will be the pressure at point 2, because now we are moving from point 2 to point 3. So our pressure at point 3 is going to be equal to, first of all, we know it's rho, so let's say rho now of oil times G times H plus the external pressure. But then we're not given the density of oil. All we're given was the specific gravity of oil. But then we know that specific gravity is equal to the density of a medium to the density of water. And we know the specific gravity, we know the density of water. So we can now find the density of oil, which is equal to 0.8 times the density of water, which is 1000, right? So that means the density of oil is 800, right? 800 kilograms per meter cube. So now we have the density of oil. We can now find the pressure at point 3, which is going to be 800 times 9.81 times the height 0.9, and plus the external pressure, which here is now the pressure at point 2, plus 20,601. When you compute everything, you are going to get 7. So you're going to get 7063.2 plus 20,607, and this should be giving you 27,663. Sorry, 26,670.2. And this we can now make this 27.67 kilonewtons. Sorry, kilonewton per meter squared, or kilopascal, because the unit for pressure is pascal. So let's take another example. So in this question, it says that, so this is the diagram. We have a fluid, and here we have the external pressure to be 50 kilopascal, and we have glycerin, and the height or the depth is 2 meters. The specific gravity of this glycerin is 1.26, and we are asked to find the pressure at the bottom. So in a case like this, your external pressure has been clearly defined. So that means your external pressure is not going to be atmospheric pressure, but the pressure that has been given to you. And so now we need to find the density of the glycerin, because you know that the formula is equal to gamma H plus P naught. which is rho g h plus p naught. And so our density here, we can say this specific gravity, this 1.26, is equal to the density of the glycerin over the density of water. And so the density of glycerin is going to be 1.26 times 1000, which is the density of water. And you are going to get 1260 as the density for water. So now, to compute this, we are going to have 1260 times 9.81 times the height, which is 2 meters, plus your external pressure, which is 50,000. And so when we compute this, we're going to have 74,721.2, which is going to be 74.7 kilo Newton per meter squared. Yes, and that is your final answer. So let's take a last question, then we move on to something else. So let's take another example. Okay, so we have a structure like this, right? And we have two fluids at different depths. So this here is open to the atmosphere, so we'll say it's open to the atmosphere. So now the question says, because of a leak in a buried gasoline storage tank, water has seeped into the depth shown below, which is this diagram. Now it says that the specific gravity of this gasoline is 0.68, and we are being asked to find the pressure at the gasoline water interface. So this is the gasoline and this is the water. So at this point, this interface, they're asking us to find the pressure at that point. Next, they're asking us to find the pressure at the bottom of the tank. So that is going to be, yes, at the bottom of the tank. Then thirdly, we are being asked to express the pressure at the gasoline water interface as pressure head in meters. So we are going to express it as pressure head in meters of the water column. So first of all, if you want to find, so first you are finding the pressure at the gasoline water interface, which is going to be this point, going to be equal to rho of gasoline times H plus P naught. And we need the density of the gasoline, which is going to be 0.68 times This is equal to 680. So now we have the density of the gasoline. The pressure is now going to be 680 times 9.81 times 17 plus 0. Since atmospheric pressure in terms of gauge pressures is 0. So this is going to be equal to this is going to be equal to 113,403.6. And so this we can say 113.4 kilonewton per meter square or kilopascal. Now we want to find the pressure at the bottom of the tank. At the bottom of the tank, it means you're going to have this pressure in the gasoline as your external pressure, and then the pressure in the water. So that's going to be for the pressure. Okay, so the total pressure in the water, which is so at the bottom of the tank, it's going to be equal to rho GH plus pressure of gasoline, which is equal to 1000 times 9.81 times 3 plus 113,403.6. Now when we add all that, we are going to get we are going to get sorry we're going to get 142,833.6, which is going to be 142.83 kilonewton per meter squared. So now that becomes the pressure at the bottom of the tank. Now the last question says if you express the pressure at the gasoline water interface, so this pressure as pressure head in meters. So you know that pressure is equal to rho GH plus P naught. Here our P naught is 0, but then they want this H. This H is the head in meters, right? And so we are going to do a change of subject. Your H is now going to be your pressure over rho G. That's going to be equal to 113,403.6 all over 680 times 9.81, and that is going to give you 17 meters. So that is basically the same as what we had in the question. Okay, so we are moving on to manometric pressure or gauge pressure. Manometric or gauge pressure is the differential pressure above atmospheric pressure at a point in the fluid. So with manometric pressure, your absolute pressure, which is your PA, here not atmospheric but absolute, is equal to your P naught plus P. This external pressure, this is gauge pressure. This is the same as the gamma H. So this is when we are working with the manometric or gauge pressure. And so we can apply this concept to many things, such as the hydraulic press. And the hydraulic press looks something like this. Please excuse my drawing. It looks something like this. And then you have this and this. These are providing the area through which the liquids can be suppressed. So this is a hydraulic press, and all there is fluid. This is fluid. So you realize that this hydraulic press has different forces that will act on top of it. So you can say this is F2, this is F1. So from Pascal's law, you say that pressure at this point and this point along the same axis are the same. So if they are the same, and we know pressure is force over area, we can say F1 over A1 equals F2 over A2. And this is the idea behind the hydraulic press. The idea behind the hydraulic press. So let's take a question. Here it says okay, for this question, okay, let me see if I can. I don't know how I'll sketch this. So let's assume we have this in the fluid. So we have the point where pressure is applied to the fluid, and then we have a fixed rigid bar which can rotate, right? So let's do it this way. We'll make this one too small this way. Okay, then we have Sorry, there was a disruption due to the network, and due to a lack of time, we'll have to end it here. But I believe you've learned enough to write your midterm. If you have any further questions, you can speak to any of your executives to reach out to any of us to help you. Thank you and all the best in your midterm. My name is Benedict.